Hello, this is Reem from Exam Hub Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2, wherein to October-November 2017. Question number 1. One end of a wire is connected to a fixed point. A load is attached to the other end so that the wire hangs vertically. The diameter D of the wire and the load F are measured as. Part A. For the measurement of the diameter of the wire, state the name of a suitable measurement instrument. So that's micrometer screw gauge. Part 2, how random errors may be reduced when using the instrument in part 1. Okay, so zero error can't be in our answer since that causes systematic error. So what we can do is we can take several readings along the length of wire and take average of those readings. So take several readings. Along the length of the wire. And take average. Part B, the stress in the wire is calculated by using the expression. Part 1 showed that the value of stress is 1.99 into 10 to the power of 8 Newton per meter square. So stress is equals to 4 into the force. The force that's being exerted on the wire is 25 newtons. So stress is equals to force multiplied by 4 divided by pi. D squared, the diameter of the wire over here is 0.4 millimeters. We'll convert that to meters. So 0.4 divided by 1000, the whole square, and that gives us 1.99 into 10 to the power of 8 Newton per meter square of stress. Part 2, determine the percentage uncertainty in the stress. So the percentage uncertainty of stress is going to be the sum of individual percentage uncertainties that are involved in the formula of the stress, and those quantities are force and diameter. So the percentage uncertainty for the quantity force is the absolute uncertainty of the force divided by the value force into 100%, and it should be added to the percentage uncertainty of D twice, because in the formula stress we are taking D twice. So the percentage uncertainty of D is going to be 0.02, the absolute uncertainty, divided by the value D, which is 0.4 millimeters, and this should be multiplied with 100% as well as with 2. And that gives us a total percentage uncertainty of stress as 12%. Part 3, use the information in B part 1 and your answer in B part 2 to determine the value of stress with its absolute uncertainty to an appropriate number of significant figures. So the absolute uncertainty is going to be the percentage uncertainty of the value stress, that's 12% from the previous part, divided by 100%, and the value of stress will be multiplied with it, and the value for stress is 1.99 into 10 to the power of 8. This gives us an absolute uncertainty of plus or minus 2.388 into 10 to the power of 7. So stress is 10 to the power 8, which is 1.99 into 10 to the power of 8. And this is in terms of 10 to the power of 7. We must have the same powers to the 10. So we will convert 10 to the power 7 of this absolute uncertainty to 10 to the power 8, so that this becomes 0.2388 into 10 to the power of 8. Now we must change this to only one significant figure. So the value stress becomes 2 into 10 to the power of 8, and the absolute uncertainty becomes 0.2 into 10 to the power of 8. We can write this 2 plus or minus 0.2 into 10 to the power of 8. Question number 2, part A, define the moment of a force. So this is force multiplied by perpendicular distance from the pivot Part B, a thin disk of radius r is supported at its center O by a pin. The disk is supported so that it is vertical. The three forces act in the plane of the disk as shown in figure 2.1. The two horizontal forces, the two horizontal and opposite forces, each of magnitude 1.2 newtons, act at points A and B on the edge of the disk. A force of 6 newtons at an angle theta below the horizontal acts on the midpoint C of a radial line of the disk, as shown in figure 2.1. The disk has negligible weight and it is in equilibrium. So the disk is in equilibrium. All the forces and moments are balanced. Part 1, state an expression in terms of R for the torque of the couple due to the forces at A and B acting on the disk. So torque is one of the two equal forces at A and B multiplied by the perpendicular distance between those two forces, and the perpendicular distance between the two forces, 1.2 newtons, is r plus r, and that's 2r. So we have the torque of the couple due to the forces at A and B as 2.4r. Part 2, friction between the disk and the pin is negligible. Determine the angle theta. So first of all, we'll calculate the clockwise moment of the disk, and this clockwise moment of the disk is being caused by the torque of the couple due to the forces at point A and B. So this is equal to 2.4r, and the anti-clockwise moment of the disk is being caused by this force, 6 newtons of magnitude. But the force that we are supposed to use over here is not the 6 newtons, but its vertical component, because we are supposed to use force and the perpendicular distance from that force to the point pivot. So the vertical component of the force, 6 newtons, is 6 sine theta, and the distance from this force's vertical component to the pivot point is r by 2. So 6 sine theta r by 2. And the disk, and remember that the disk is in equilibrium state, so 2.4r is equals to r by 2, where r and r gets cancelled, so sine theta becomes 4.8 divided by 6, hence the value for theta is 53 degrees. Part 3, state the magnitude of the force of the pin on the disk. So since the disk is at equilibrium state, this force must be equal to the force that's being exerted at this point, and it's 6 newtons. So 6 newtons of force. Question number 3, a spring is attached at one end to a fixed point and hangs vertically with a cube attached to the other end. The cube is initially held so that the spring has 0 extension. The cube has weight 4 newtons and size of length 5.1 centimeters. The cube is released and it sinks into water as the spring extends. The cube reaches equilibrium with its base at a depth of 7 centimeters below the water surface, as shown in figure 3.2. The density of the water is 1000 kilograms per meter cube. Part A, calculate the difference in pressure exerted by the water on the bottom face and on the top face of the cube. Okay, so on the bottom face of the cube, the depth of the water is 7 centimeters or 0.07 meters. So pressure at that point on the cube is going to be equal to the density of the water multiplied by the value 9.81 into the depth of the water, that is 0.07. And if we talk about the top face of the cube, the depth of the water is 7 centimeters minus 5.1, since this is the length of the cube, which is 5.1 centimeters. So pressure that is exerted on top of the cube is going to be equal to, again, 1000 multiplied by 9.81 into depth, that is 1.9 centimeters. I converted that to meters, and the difference in pressure is going to be of 500 pascals. Part B, use your answer in part A to show that the upthrust on the cube is 1.3 newtons. Okay, so upthrust is always due to change in pressure, so upthrust is equals to that change in pressure, which is 500 pascals, multiplied by the area of the cube. That can be calculated by multiplying length and breadth. So 5.1 centimeters into 5.1 centimeters, and later convert that to meters squared. So we will have a cross-sectional area of cube as 2.6 into 10 to the power of negative 3 meters squared. When we get the product of it, the upthrust is 1.3 newtons. Part C, calculate the force exerted on the spring by the cube when it is in equilibrium in the water. So when it is in equilibrium, the force that acts downwards is going to be the weight, and upthrust is going to act upwards, and this force is also going to act upwards. So as the cube is in equilibrium, the sum of upthrust and this force must be equal to the cube's weight. Hence, the value for this force that is exerted by the cube on the spring is going to be the difference between the weight and the upthrust, that is 1.3 newtons. Hence, this force is of 2.7 newtons of magnitude. Part D, the spring obeys Hooke's law and has a spring constant of 30 newtons per meter. Determine the initial height above the water surface of the base of the cube before it was released. So we're going to use the formula force is equals to spring constant into extension, where the force that's exerted onto the spring by the cube is 2.7 newtons and the spring constant is 30 newtons per meter and extension is unknown. So here we get to know that extension is of 0.09 meters in total. This means that when the cube was released, after it was held initially when the spring had zero extension, when this cube was released, it undergoes an extension of 0.09 meters, or I should say 9 centimeters of extension. So when it reaches equilibrium, it had a total extension of 9 centimeters. And over here, you know that cube has reached equilibrium when its base is at a depth of 7 centimeters below the water surface. So this means that this is the distance that it travels before it touches the water surface. So this is going to be the difference between this extension that it undergoes and the depth when it reaches equilibrium state. So 9 minus 7, that's 2 centimeters. So 9 centimeters, which is the total extension that it undergoes when a magnitude of 2.7 newtons of force is exerted on the spring. And when it reaches equilibrium state, it had a depth of 7 centimeters below the water surface. So in total, it had a 2 centimeters of height above the water surface when it was released. Part E, the cube in the water is released from the spring. Determine the initial acceleration of the cube. So first of all, we need to know the mass of the cube. This is equal to the weight of the cube divided by the value g. And the force that's exerted by cube is 2.7 newtons. So this is the mass. Now force that's exerted by the cube on the spring is 2.7 newtons. This is equals to the mass of the cube multiplied by the acceleration. Hence the initial acceleration of the cube is of 6.6 meters per second square. Part 2, describe and explain the variation, if any, of the acceleration of the cube as it sinks in the water. So acceleration of the cube will decrease because with time the drag or the viscous force that acts on the block will increase, which reduces magnitude of the resultant force. And you know that resultant force is directly proportional to acceleration. So acceleration decreases as viscous force increases with time. Which reduces resultant force. Question number 4, part A, state the conditions required for the formation of a stationary wave. So for a stationary wave to form, we need to have two incoming waves that are traveling in opposite directions, and they must have the same wavelength or frequency, and those two waves must overlap each other. So two waves with same frequency and traveling in opposite directions must overlap. Part B, a horizontal string is stretched between two fixed points x and y. The string is made to vibrate vertically so that a stationary wave is formed. At one instant, each particle of the string is at its maximum displacement as shown in figure 4.1. P and Q are two particles of the string. The string vibrates with a frequency of 40 Hz. Distance xy is 2 meters. Part 1 state the number of antinodes in the stationary wave. So these are all the points that are antinodes. They have maximum amplitude. So in total we have 5 antinodes on the stationary wave that are forming. Part 2, determine the minimum time taken for the particle P to travel from its lowest point to its highest point. Okay, so the frequency of the string vibration is 40 Hz. This means that the time interval is going to be of 1 over 40, and that's 0.025 seconds. And this means that this is the time interval in which particle P will travel to adjacent lowest or highest point. So to travel from its lowest to highest point, it will take 0.025 divided by 2, since it is traveling half of its wavelength. So that will take 0.0125 seconds. Part 3, state the phase difference with its unit between the vibrations of particle P and of particle Q. So between particle P and particle Q, there is a node, which means that P and Q, they are out of phase and they have a phase difference of 180 degrees. Part 4, determine the speed of a progressive wave along the string. So the speed of a wave is equals to its frequency multiplied by the wavelength, where frequency is 40 Hz and the wavelength is this measure from point X until this point. And it is told that from point X to Y, this length is 2 meters in total. And this comprises of 1, 2, and half. So 2.5 wavelength measures 2 meters, hence the wavelength is going to be of 0.8 meters. So speed is equals to 40 into 0.8, and that's equals to 32 meters per second. Question number 5, part A, define the coulomb. They're asking you to define the unit for the charge. So charge is equals to current into time, so coulomb is going to be ampere second. Part B is two vertical metal plates in a vacuum have a separation of 4 centimeters. A potential difference of 2 into 10 to the power of 2 volts is applied between the plates. Figure 5.1 shows a side view of this arrangement. The smoke particle is in the uniform electric field between the plates. The particle has weight 3.9 into 10 to the power of negative 15 newtons and charge negative. Part 1 show that the electric force acting on the particle is 4 into 10 to the power of negative 15 newtons. So electric force divided by the charge is going to be equal to the change in voltage divided by the distance between the charged plates. So force is equals to, electric force is equals to the voltage difference, and that's of 2 into 10 to the power of 2 multiplied by the charge of the smoke particle, and that's 8 into 10 to the power of negative 19 coulombs divided by the distance between the charged plates, that's 4 centimeters. So we'll convert that to meters. Hence we have the electric force as 4 into 10 to the power of negative 15 newtons. Part 2, on figure 5.1, draw labeled arrows to show the directions of the two forces acting on the smoke particle. So there's always weight that acts vertically downwards, and there's going to be the force on the particle due to electric field towards the more positively charged plate. This is the positively charged plate, and this is a negative particle, so this will be attracted towards this charged plate. This is weight and this is the electric force. Part 3, the resultant force acting on the particle is F. Determine the magnitude of F. Okay, so there is a force that acts on smoke particle towards the left, and it has a magnitude of 4 into 10 to the power of negative 15. This is due to the electric field. And then there is a weight that acts downwards, and it has a magnitude of 3.9 into 10 to the power of negative 15 newtons. And the resultant force is going to be calculated by using the Pythagoras theorem. So this is equals to root of the squares of these forces. So the magnitude of the resultant force that acts on the smoke particle is 5.59 into 10 to the power of negative 15 newtons. the angle of F to the horizontal. So this is the force F, and this is the angle they're asking you to calculate. So we'll use the formula tan theta is equals to the opposite of the angle, that's 3.9 into 10 to the power of negative 15, at the adjacent, that is 4 into 10 to the power of negative 15, and the theta is going to be of 44 degrees. Part C, the electric field in part B is switched on at time t is equals to 0 when the particle is at a horizontal displacement 2 centimeters from the left-hand plate. So suppose this is the left-hand plate with a positive charge, and this is earthed, so this carries a negative charge. This in total is a distance of 4 centimeters, and it says that the smoke particle is at a displacement of 2 centimeters, means it is exactly in the middle. So this is the distance, 2 centimeters. When the electric field is switched on at time t is equals to 0, it will be traveling towards the positively charged plate, since this carries a negative charge, and it will be attracted towards its opposite charge. The particle is then moved. The horizontal at time t is equals to 0, the horizontal velocity of the particle is 0. The particle is then moved by the electric field until it hits a plate at time t is equals to capital T. So it takes time t to travel from the midpoint to the positively charged plate. Sketch the variation with time t of the horizontal displacement of the particle from the left-hand plate. So at time t is equals to 0, displacement is 2 centimeters. So at t is equals to 0, the displacement is 2 centimeters, and at time t is equals to capital T, the displacement will be 0 since it has reached the positively charged plate. Capital T, we are going to have 0. And since it's going to accelerate because it has a resultant force of 5.59 into 10 to the power of negative 15 newtons acting on it. So acceleration, how can we show acceleration on displacement versus time graph? We are going to have an increasing gradient, but a downward slope. So we are going to have an increasing curve with a positive gradient. The steeper the graph gets, the higher the gradient becomes. Question number 6, part A, state what is meant by an electric current. So a current is flow of charge carriers. Part B, a metal wire has length L and cross-sectional area A as shown in figure 6.1. Part 1, state in terms of A, E, L, and N an expression for the total charge of the free electrons in the wire. So the total charge of the free electrons in the wire is going to be the number of electrons into the single charge, into cross-sectional area, and into length. Part 2, use your answer in part 1 to show that the current is given by the equation. So current is equals to charge divided by time. The total charge of the free electrons in the wire is equals to NEAL divided by time, where this L by T, that's distance by time, is equals to NEA into the drift velocity of the charge carriers. So I becomes NEAV. Part C, a metal wire in a circuit is damaged. The resistivity of the metal is unchanged, but the cross-sectional area of the wire is reduced over a length of 3 millimeters, as shown in figure 6.2. The wire has diameter D at cross-section X and diameter 0.69 D at cross-section Y. The current in the wire is 0.5 amperes. Part 1, determine the ratio of the average drift speed of free electrons at cross-section Y and that at cross-section X. Okay, so I is equals to NAVE, where current across cross-section Y and X, and the number of free electrons across cross-section Y and X, they are going to remain the same. So we can ignore I, N, and E. So we're going to have the drift velocity is equals to 1 by A. So this means that the drift velocity is inversely proportional to cross-sectional area. The drift velocity of section X is going to be 1 divided by the cross-sectional area of section X. So section X has an area of pi d squared by 4. Area is pi d squared by 4. In terms of the area is pi d squared by 4. So 1 divided by pi d squared by 4, this becomes 4 by pi d squared. Now average drift speed at across cross section Y is going to be equal to 1 divided by the cross section area of section Y. So this is going to be pi 0.69 d square by 4. So 1 divided by pi 0.69 d square by 4. So this becomes 4 divided by 0.4761 pi d square. Now when you divide the average of speed at cross-section Y with average of speed of free electrons at cross-section X, this is going to become 4 divided by 0.4761 pi d square multiplied by pi d square by 4. So 4 and 4 gets cancelled, pi d square, pi d square. So 1 over 0.4761 will give you a ratio of 2.1. Part 2, for the damaged length of the wire, calculate the resistance per unit length. So resistance is equals to resistivity into length by cross-sectional area, where the resistance and the length of both the wires, they remain the same. So we can take resistivity by cross-sectional area is equals to resistivity by cross-sectional area, where this resistivity is at X and X, this is Y and Y. Now resistivity at cross-section X is equals to 1.7 into 10 to the power of negative 2, and the area of cross-section X is pi d square by 4. This is equals to resistivity at cross-section Y, which is what we are asked to calculate, divided by the area of the cross-section Y, which is 0.69 d square by 4. And when you rearrange your formula, you will get the resistivity of cross-section Y as 3.6 into 10 to the power of negative 2 ohm per meter. The power dissipated for the damaged length of the wire. So power dissipation is equals to I squared by R. The current that passes through that cross-section area Y is equals to 0.5 square multiplied by the resistance of the length of that cross-section area. Since the resistivity of that cross-section area is 3.6 into 10 to the power of negative 2 ohm per meter, and the length of the cross-section area Y is 3 millimeters, which will convert that to meters, so 3 into 10 to the power of negative 3 meters. This gets a resistance of 3.6 into 10 to the power of negative 2 multiplied by 3 into 10 to the power of negative 3. This is the amount of resistance of the cross-section Y. So when you multiply this with 0.5 square, you will get the power dissipation for the damaged length of the wire as 2.7 into 10 to the power of negative 5 watts. Part 3, the diameter of the damaged length of the wire is further decreased. Assume that the current in the wire remains constant. State and explain qualitatively the change, if any, to the power dissipated in the damaged length of the wire. Okay, so since R is inversely proportional to cross-sectional area, we are going to have here the resistance increasing, and as a result, power dissipation will increase too. So resistance increases. Question number 7, a stationary nucleus X decays by emitting a beta plus particle to form a nucleus of carbon-13. An incomplete equation to represent this decay is this one. Part A, state the name of the class of particles that includes a beta plus particle. So this is beta plus, and that's leptons. Part B, for nucleus X, state the number of protons and neutrons. So the mass number over here is going to be 13, since beta plus particle has a mass number of 0 and a proton number of +1. We're going to have proton number over here as 7. So the number of protons is 7, and the number of neutrons is the difference between these two values. So 13 minus 7, this is 6. Part C, the carbon-13 nucleus has a mass of 2.2 into 10 to the power of negative 26 kilograms. Its kinetic energy as a result of the decay process is 0.8 mega electron volt. Calculate the speed of this nucleus. So kinetic energy is equals to half mv square, where the amount of energy, we must convert this to joules. So 0.8 into 10 to the power of 6 electron volt. First we will convert that to electron volt for mega, and each electron volt has 1.6 into 10 to the power of negative 19 joules of energy. So we'll multiply 0.8 into 10 to the power of 6 into 1.6 into 10 to the power of negative 19 to convert electron volt to joule. So this is the amount of energy with which carbon-13 nucleus is given off. Now 0.8 into 10 to the power of 6 into 1.6 into 10 to the power of negative 19 is equals to half into mass of carbon-13 nucleus is 2.2 into 10 to the power of negative 26 multiplied by speed square. So the speed of this nucleus is going to be 3.4 into 10 to the power of 6 meters per second. Part D explain why the sum of the kinetic energies of the carbon-13 nucleus and the beta plus particle cannot be equal to the total energy released by the decay process. So in a decay of beta plus particle, a neutrino is also produced, which also gets some amount of energy. Hence, the total of kinetic energy of carbon and beta plus particle is not going to be equal to the amount of energy that's totally released from this stationary nucleus X, because some energy is also given to the neutrino that is released. So a neutrino is also produced, which also gets some energy.